Alright, so
we're suffering from the heat here.
prove.
It's really warm, so we're not gonna make a big video.
We're gonna prove.
What are we gonna prove?
That.
This. And that is that a Fibonacci number is... What?
The sum of its neighboring...
equals the sum of its neighboring...
Luca
numbers over 5.
Over 5, yeah.
And this is what you're gonna prove.
Yeah.
And this proof you got from where?
I've made it myself.
You made it yourself.
That's why we're making a video in the first place.
Oh, okay. I know, I'm kidding. But you just told me like a minute ago. That's why I said make a video.
Yeah.
Because I'm always saying make a video if it's your own
and now
proof.
we have more colorful whiteboard markers. I had to find the color harder. So basically, what we're gonna do is we're gonna prove that this holds for all positive integers, all integer greater than 2. Because,
Okay.
Well, we're actually greater than 1 even is gonna work, but well, little greater than 2. Basically we've got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the way we're going to prove this is by using a proof by induction. So what is a proof by induction? So first, we'll check the first 2 cases. So for 2 and 3. Normally you check only the first case, but it's hard to do just the first case and prove everything from that. And so I'm gonna check the first 2 cases. This is what's called the base case. Fancy name. So basically, if we have any number, and the second thing we're going to prove is that if this thing holds for any number n minus 1, and it holds for any number n, then it will also hold for n plus 1. If holds for that and
It's way too small. I can't read it.
that and that, then holds for
7. Слишком мелко, ничего невозможно прочесть. Это никто не сможет прочитать.
She's whispering to me in Russian. If it holds for that and that, so if holds for that and that, see? Then it holds for that.
So if it holds for n minus 1 and n, it also holds for n plus 1.
So that's one thing we're going to prove. It's called the induction case. The other thing we're going to prove is just the first 2 cases, so we can guarantee it works. Just with a bit of common sense, you can actually prove that this is a complete recipe for proving something. So, it's called proof by induction. So now, let's begin our proof by induction was just checking the first two cases. So for a equals 2, okay, L1 is 1. So let me just write out the first few. There are more Fibonacci numbers than I know Luca's numbers. Luke got numbers.
But here you've got them.
Here I've got them, but anyway, so I'll just list them out. So we've got 1, 3, 4, 7, 11, 18, 29, 47, and so on.
Those are
The Luca
numbers.
The Fibonacci numbers, well, they start, well, I don't think it was 1, 1. And then we've got 2, 3, 5, 8, 13, 21.
The 3 looks like a 1.
It's kind of like a flattened 3. I don't know. That looks more like a 3.
Yeah, okay.
So, let's check the first two cases. And so we do a kind of V shape. Or upside down V. So, 1 plus 4 divided by 5 is 1. Good. And 3 plus 7 divided by 5 is 2. Great.
So it works.
It works. I in my head put in parentheses in, so it's.
So you know the order of operations.
Yeah, so it's like 1 plus 4 divided by 5, and 3 plus 7 divided by 5. Okay. Okay. So.
Yeah, and now you've got to do the second part, right?
I gotta do the second part. That's more complicated, and I've got it at the.
And this is what you've already
got it
been
at the
doing.
bottom here. We assume it's true for n minus 1, and it's true for n. And we want to prove that it's true for n plus 1.
Mm-hmm. This is what you want to prove. But then you're writing ln plus 2.
Divided by 5. So that's the expression if we substitute n plus 1 in. So if we put n plus 1 into the equation, on the right-hand side is going to look like this. So, it's helpful to start from the more complicated side, because, yeah, then you're gonna be able to, really simplify and make it easier. So we start with that expression, but Ln plus 2, well, that's the same as a Fibonacci action. That plus that equals that. That plus that equals that. That plus that equals that. So Ln plus 2 is then just Ln plus Ln plus 1. So basically we've now got this expression here. Well, hang on. Ln is just Ln minus 2 plus Ln minus 1, right? So now I've got this list of 4 numbers here divided by 5. An entire list divided by 5, so it's important to do the order of operations correctly. You have to put the brackets in here, not put in no brackets at all. So, not put in any brackets at all. You have to put the brackets in there. So,
but you didn't.
I didn't, but the fraction sign indicates it.
Oh, okay.
My helpful notation use the fraction sign since it's slash, which automatically puts in the brackets where I want them to. So, where I want them. So the brackets are here, around there. I could have put the brackets in, but again, if I didn't put in the brackets, I just would just divided one of these by 5. Put the made the fraction side shorter or longer. So, yeah, some introduction to my notation here. Now we split it up into 2 parts, this and this. Hey, but hang on. We've assumed that that's just fn minus 1 plus fn, which obviously is fn plus 1. So we've proven that it is true. There. It is true. If it holds for that, and it holds for that, then it holds for that. So if it holds for that, and it holds for that, then it holds for that, right? So if it holds for that, we just check that. So that means it holds for that. But so it holds for that, which means it must hold for that. Holds for that, it holds for that, okay? Must hold for that, and so on.
But it has been proven before, hasn't it?
Yeah, it has been proven before. Probably I haven't come up with. I probably have accidentally recreated it as always what you're doing mathematics.
What I don't understand is why you actually decided to start with this and not with this identity.
Started with
so
this,
basically,
because I put n plus 1 into the equation instead of n.
Yeah, but why?
Because we've assumed it is true for n, so it doesn't require proving it.
Ah.
We assume it's true for n minus 1 and for n, and then based on that, we've proven it's true for n plus 1.
And you're allowed to assume stuff?
I'm allowed to assume stuff if I check. I check some of the cases. So if I check 2 and 3, okay.
Oh, now I get
so
it.
Now,
yeah.
So it works for 4. Oh,
all right.
It works for 3 and 4. So then it works for 5. It works for 4 and 5. Then it works for 6. It works for 5 and 6. So then it works for 7, and so on.
Thank you.